Okay, students, in the previous videos we discussed about the sharpness of a resonant circuit, and I demonstrated that the bandwidth was equal to twice of B, that was the damping coefficient of the system. So if you have a high damped or damping system, if you have very high damping, then the bandwidth is going to be high, which means that the circuit or the system is not very selective about the frequencies. So beyond the resonant frequencies, if the frequency is way beyond the resonant frequencies, maybe the power delivered to the system will be high, and if the bandwidth is very, very small, which implies that the circuit is very selective, which means that it will deliver power only within a very small range of specified frequencies. Now, let us discuss one very important circuit, that is an LCR circuit. This is the AC voltage applied. You can see that the voltage, AC voltage, has a frequency omega. The inductance L, resistance R, and capacitance is applied in the circuit. Now if you apply Kirchhoff's voltage law, you get L di by dt, that's the voltage across this, plus IR, the voltage across this, and Q by C is the voltage across this, must be equal to this voltage. Now we know that I, the current, is dq by dt, so replacing di by dt as d square q by dt square, I is dq by dt and q by c is there. Now just divide by L throughout, you will get dq square by dt square plus R by L plus q by LC is equals to V0 by L e to the power of I omega t. Now please recall this equation. You had a very, very similar equation in forced oscillation. So the analogous equation, you remember the forced oscillation, it was d square x by dt square plus 2b dx by dt, d square q by dt square, d square x by dt square, dq by dt, dx by dt, x q, V0 by L, F0 by M e to the power of I omega t. Can you see a very, very similar equation? This is similar to this equation, where x is nothing but, in this case it is q. So in basically q is the charge across the capacitor plates. So this differential equation tells us how is q changing with time across the capacitor plates, because the voltage is changing with time, so the charges across the capacitor plates will also change with time, and this is the differential equation which governs that change of the charge with respect to time. And this is a very, very similar equation to this. So this is nothing but a forced oscillation that is happening in this circuit. So you see that if I take the analogy, then what is 2B? That is damping. So damping in the circuit 2B is nothing but R by L. And what is omega naught square? Omega naught square is nothing but 1 by LC. So what is omega naught? The natural frequency of oscillation. It is 1 by root of LC. This you have studied in your high school physics. If you have an LC circuit, the frequency of oscillation of the LC, natural frequency of oscillation, will be 1 by root of LC, the angular frequency, of course. And what about the damping? Twice of B, the damping coefficient, is equal to R by L. So it depends upon the resistance. So look at the analogy. L is nothing but the mass. It is analogous to the mass or the inertia of the body. If you remember, this was all mass, inertia of the body. R, resistance, is equivalent to losses or damping. You can see this. And capacitor C is nothing but the storage property, this one, omega naught square, this one. So you can see definitely the inductance must be analogous to mass, because if you remember what inductance tells you, in an inductor, if you try to increase the current, it will try to oppose that increase because of the electromagnetic induction, Faraday's law of electromagnetic induction. So if you try to increase the current, then there will be a voltage induced in that inductor which will try to oppose that change. So any change in current that you try to introduce in an inductor, it will try to oppose that change, and that is nothing but a property of mass also. Mass inertia is nothing but if you try to change that the state of rest or state of motion of any body, it is that inertia which will try to resist that change. So more the mass, the more is the resistance towards that change. So inductance, again I repeat, in an inductor, if you try to change that current, a voltage will be induced that will try to oppose that change, and similarly is for mass. So inductance and mass are equivalent. Resistance, definitely it is the loss, because whenever you have a resistance in a circuit, there are ohmic losses or heating losses. Whenever current passes through a resistor, heat energy is lost as heat, and that is nothing but damping that we were dealing with. So in an electrical circuit, inductor corresponds to the mass, resistance corresponds to damping, and capacitance is definitely, you know, it is used for storing charges. It is the spring, it is behaving the spring. So if you compress a spring, it will store energy. Similarly, capacitor, if you store charges, basically capacitor is required for storing charges. So it is or storing energy, electrical energy. So this is storing electrical energy, like the spring which was storing potential energy. So these are the analogous terms. So basically what you have is, you have a differential equation which was same as the forced vibration. This was the external force, this is the external voltage. In this case, this is the force applied, and you know the solution, what the solution is. But we'll be dealing with these quantities. Now please understand, given a circuit, for a given circuit, let's say the inductance is given as 1 microhenry and capacitance is given as 1 picofarad and resistance is 1 ohm. Let us find out this is an example. Let us find out the natural frequency of oscillation. What is omega naught? Omega naught is 1 by root of LC. L is this, C is this. So this becomes root of 10 to the power of minus 18, and this becomes 10 to the power of minus 9. So 10 to the power of minus 9 goes up, it is 10 to the power of 9 radians per second, omega naught. So what is nu naught? That is the frequency. This is the angular frequency. It is omega naught by 2 pi, which is 10 to the power of 9 by 2 pi, and it is 159 into 10 to the power of 6 hertz. You can calculate it yourself, which is 159 megahertz. You can see this frequency megahertz is in radio frequency range, and this around this frequency we hear FM in our radios. So FM is again 98.3 megahertz, 100 megahertz, 104 megahertz. So megahertz is the frequency range in which our radio stations broadcast their radio waves, and they are nothing but electromagnetic waves. This you know, that radio waves are also electromagnetic waves, that is oscillation of electric field and magnetic field. So if that falls on this circuit, so a radio wave, if it falls on the radio circuit, when will the power be maximally delivered? So that is the external force that I'm talking about, the radio waves. That is the external force that I'm talking about, and the frequency of that is around 150 megahertz, let us say, the radio waves. When will resonance take place? When this omega will be equal to omega naught. And omega naught depends on the value of inductance and capacitance, right? So what you're doing is, the radio wave is falling on the circuit, but that radio wave, let's say the frequency of that radio wave is not matching with the natural frequency of this circuit. So it will not, you know from resonance that if it does not match, then the power will not be delivered much. So there will be very low current through the circuit, and the circuit will be approximately off. But if I somehow change the inductor, or if I somehow change the capacitor, that is if I adjust the L and C value so that the omega naught value changes and it matches with the frequency of this radio wave, then there will be resonance in this circuit and maximum power will be delivered in the circuit, and your circuit will work. And this is how your radios work. When you change in your old radios, what you have is, you had a pot, which you rotated so that you could tune into a radio station. And when you were rotating that pot, you were basically changing the inductance or the capacitance of the circuit. So you were changing the natural frequency of this circuit, and you were matching that natural frequency with the radio wave frequency that was coming. So you were basically tuning that, and that was called the tuning of your radio. And you were basically tuning means you are changing the L and C value of your circuit, radio circuit, so that the natural frequency matched with that of the frequency of the incoming radio wave. So now we have seen that if I take these values for inductance and capacitance, the natural frequency will be in megahertz range. Now what about the bandwidth? We know 2B is the bandwidth, that is R by L, and R I have taken as 1 ohm and L is 10 to the power minus 6 Henry. So this becomes 10 to the power of 6 radians per second, and that is delta omega. That's the bandwidth. So in terms of delta nu, that is frequency, it is 10 to the power of 6 divided by 2 pi, because delta omega by 2 pi. So I have 1.159 megahertz. So delta nu becomes 0.159 megahertz. So this means that the natural frequency was 159 megahertz and the bandwidth is 0.159 megahertz, which means if I subtract this and if I add this, I'll get 159.159 megahertz, and if I subtract this, I'll get 158.841 megahertz. So it is within this frequency range that the power delivered will be maximum. If you go, bandwidth means this. So if you go below this, the power delivered to the system will be low. And if you go higher than this, the power delivered to the system will be again low. So in between this that's the bandwidth. In between this frequency, the power delivered to the system is large. You remember that it is at these frequencies where the power goes down by 70%. We did it in the previous videos. So it is at these frequencies that the power goes down by 70%. So if you go below this, the power is still lower, and if you go above this, the power is still lower. So we can approximately say that within this range, that is the bandwidth, within this range of frequencies, the power delivered to the system is maximum. So this finishes up your oscillation, free, damped and forced oscillation, and this is how LCR circuit or tuning is done. Electrical circuit, the analogous electrical circuit, this is analogous to the forced vibration. So that finishes up your oscillation part. Thank you.